Problem 1, find the steady state error for unity feedback control system whose g of s is given by 10 by s into s plus 2 for the following inputs: 10 u of t, 10 t u of t, 10 t square u of t, 1 plus t of u of t, 1 plus t square u of t. Consider a unity feedback control system whose g of s is given by this, and such a system when excited by these inputs, what will be the steady state error? As you are aware that this signal 10 u of t whose Laplace transform is 10 by s. It is a step signal but not of unit step, it is 10 by s. For such an input, if you want to calculate steady state error, the formula was given earlier. It is 1 by 1 plus kp, where kp is position error constant, and this is calculated by using the formula limit s tending to 0 the given function g of s. Now, if you substitute in this 10 by limit s tending to 0 s into s plus 2, so when you substitute s tending to 0, then this becomes infinite. That means position error constant is infinite for unit step input. Now, the steady state error ESS will be 1 by 1 plus infinity, and it is 0. So, there is no steady state error for this system when it is excited by a step input of 10 u of t. Same system when excited by a ramp input, the second case. Let us look at this second case. The input is 10 t, means ramp input applied to this system. Then what is the steady state error? So, Laplace transform of this ramp input 10 t is 10 by s square, and the steady state error for this input is calculated using the formula 10 by kV. If it is a unit step or unit ramp, there is no numerator term, only 1 will be there, but now it is a 10 times t. So, the steady state error is given by the formula 10 by kV, where kV is limit s tending to 0 s times g of s. Substitute g of s, this function, then and s tending to 0 here, kV will be 5. So, now the steady state error is 10 by 5, it is 2. So, it is a finite error. The steady state error is finite for ramp input, whereas for step input it is 0. So, now let us apply the third signal, parabolic input, to the g of s. So, let us see the steady state error for parabolic input, and the Laplace transform of this parabolic input is 20 by s cube. And for such an input, what is the steady state error? So, case 3, the input is 20 by s cube, it is a parabolic input. Let us see the steady state error for parabolic input whose Laplace transform is 20 by s cube. The formula for steady state error is 20 by Ka, where Ka is limit s tending to 0 s square g of s. Now, limit s tending to 0 s square, and the function is 10 by s into s plus 2. So, there is s in the numerator. So, this Ka will be 0 anyway, and if you see the steady state error ESS, it is infinite. So, for parabolic input, the steady state error is infinity. Now, you look at the beauty of fourth and fifth part, that step and ramp are combined. Previously, in the first three cases, individual inputs, step, ramp and parabolic. Now, if step and ramp are combined, what is the steady state error? So, as you know, in the case of 4, the input is 1 plus t into u of t. So, 1 u of t means it is step input. So, that step input we have already seen whose steady state error is 0. So, for this 1 plus t u of t combining step and ramp, and for the first part the steady state error is 0 anyway, and the second one is t. It is not 10t, but it is simply t, whose Laplace transform is 1 by s square. So, the steady state error for this part, of the signal is ESS is equal to 1 by kV. So, 1 there in the numerator because it is simply t, not 10t. Now, as you know, kV is limit s tending to 0 s times g of s. So, if you substitute 0 in the function, s and s gets cancelled, and this kV will be 5. So, the steady state error will be 1 by 5 and it is 0.2. So, even if the signals are combined, you should calculate the steady state error for individual inputs and you can combine them. Now, if you look at the fifth signal, it is combining all the 3 inputs like step, ramp and parabolic. So, we have already seen that for this step signal the steady state error is 0, and for ramp input we have seen it is 0.2, and for t square, that is parabolic input, the steady state error is infinite. So, when you combine this, the steady state error for this particular signal applied to this system, it will be infinity. So, this is the way the problem will appear to calculate steady state error for this kind of inputs is to be solved in this way. Second problem, for the given block diagram, it is a unity feedback control system. Find out the steady state error if input is unit step. This is another variety of problem that appear on steady state error. It is to be calculated for unit step input. You can see that it is a unity feedback control system whose h of s is equal to 1 here, and these 2 blocks are in cascade. So, we need to combine them to find the g of the system. So, these 2 blocks are in cascade. So, product of that will be the g of s. Product of these 2 will be the g of s. So, 15 into 345 by s plus 1 into s plus 15. So, this is the function now. So, as you know that the moment when unit step input and steady state error, ESS is given by 1 by 1 plus Kp, where Kp is the position error constant, and this is to be calculated using limit s tending to 0 g of s. Now, the function is this 45 by s plus 1 into s plus 15. So, when you substitute 0 here, this become 45 by 15, it is 3. So, the position error constant is 3 and steady state error is 1 by 1 plus that constant 3. So, it is 1 by 4, it is 0.25. So, when blocks are given in this way, you need to calculate the steady state error. After combining the 2 blocks, find Kp and then steady state error, it is 0.25. So, the meaning of this, it is a system of second order and you got the steady state error of 0.25. What does it mean? The nature of the input you have given is a step and it is of unit step 1 r of t. Now, the response, system response will have oscillations and finally it settles in the steady state, and this 0.25 exists. this 0.25 exists between the desired and actual. That is the meaning of steady state error. G of S of unity feedback control system is given by K by S into S plus 1 into S plus 2, and the steady state error is also given for this system as 0.1 for unit ramp input. Then find the value of K. So, you can look at this, the given function G of S has got K, and steady state error is also given here. We need not calculate. Steady state error is given 0.1 for unit ramp input. Then what is the value of K? So, when it is said as unit ramp input, the steady state error ESS is 1 by kV, because it is unit ramp. So 1 by kV, where kV is, as you know, limit S tending to 0, S times G of S. So, this steady state error is given in the problem, it is equal to 0.1. Now, we need to evaluate for K. So, when you see now kV, limit S tending to 0, S times the given function which has K, S into S plus 1 into S plus 2. Now, this S and S gets cancelled, and S tending to 0, this leads to K by 2. kV is equal to K by 2. Now, substitute this K by 2 here, that is a velocity error constant. So, 1 by K by 2 is 0.1. So, you can now calculate the value of K. This is K, from this it will be 20. So, when you see, because here you are not asked to calculate the steady state error. Remember, we are going in a reverse way, that steady state error is given and you are trying to get the value of kV and hence the value of K. So, this is the way you should calculate K value when steady state error is given. Determine the steady state error for unit step, unit ramp and unit parabolic inputs for the given system described by the block diagram. So, look at the block diagram here. You can see that there is a component in the feedback also. Generally, we consider this as G, and this one we consider as H. So, the steady state error is defined as the error between the reference input and the actual output. So, such a system is given, it is a non-unity feedback control system. So, we need to convert that into unity feedback control system. When G is given, H is given, then we need to convert this non-unity feedback control system to unity feedback control system. Means there is only one block in the forward path and no element in the feedback path. So, this H, now when you make 1 in the feedback path, the formula here is G by 1 plus GH minus G, where G is 2 by S plus 6 and H is 2 in this problem. So, substitute here that G is 2 by S plus 6 by 1 plus G is 2 by S plus 6, H is 2 minus G again, G is 2 by S plus 6. So, when you try to simplify this, 2 by S plus 6, then this one, the S plus 6 is the LCM and that comes here in the numerator. This is 4, then minus 2. So, 4 plus 6 10 and then minus 2 8. So, this will be 2 by s plus 8. So, that function you need to write here, because steady state error is the error between reference input and actual output and unity feedback control system. So, when you transform this non-unity feedback control system into unity feedback using this formula g by 1 plus gh minus g, the function becomes 2 by s plus 8. Now, you consider this as g for this unity feedback control system. So, the question is now for unit step input, what is the steady state error? So, again using the formula ESS is equal to 1 by 1 plus Kp, where Kp is limit s tending to 0 2 by s plus 8. So, this becomes 2 by 8 means 1 by 4 is the Kp, that you need to substitute here 1 by 1 plus 1 by 4. So, this will be 0.2. So, the steady state error for non-unity feedback control system is to be calculated in this way, and you have got 0.2 steady state error for unit step input. Now, the second case, the steady state error for unit ramp input. So, it is given by ESS equal to 1 by Kv, velocity error constant, where Kv is limit s tending to 0 s times this function 2 by s plus 8. So, Kv becomes 0 in this case. So, the steady state error is infinity. So, even if you calculate for unit parabolic input, in the third case it is 1 by Ka for parabolic input, where Ka is limit s tending to 0 s square g of s. So, you have 0 in the numerator itself, and Ka also will be 0, the acceleration error constant. So, the steady state error is infinite. So, please remember that once you get steady state error of some finite magnitude 0.2 for unit step input, and for the rest of the inputs ramp and parabolic, the steady state error will be infinity. So, this is the way you should remember the steady state error for various inputs. The given problem is d square x by dt square plus 6 dx by dt plus 5x is equal to 12 into 1 minus e power minus 2t. For such a system, you are asked to find out the response as time tending to infinity. So, let us see how to calculate the response as time tending to infinity. According to the final value theorem, limit t tending to infinity f of t is equal to limit s tending to 0 s times f of s. This is according to final value theorem. So, you can use either this or this. Now, when you look at this differential equation, let us apply the Laplace transform to this function. Then it becomes s square x of s plus 6 s x of s plus 5 x of s is equal to 12, whose Laplace transform is 12 by s minus 12 by exponential term whose Laplace transform is s plus 2. Now, x of s is common here, x of s square plus 6s plus 5 is equal to s into s plus 2 in the denominator. Then this is 12 into s plus 2 minus 12s. So, this will be, these two gets cancelled, this is 24 by s into s plus 2. Now, x of s I want to know. So take this term to the right hand side, 24 by s into s plus 2 into s square plus 6s plus 5. Now you have got x of s like this. The question is, what is the response x of t as time tending to infinity? It is same as limit s tending to 0 s into x of s. So now I want to find out the response. So this is equal to limit s tending to 0 according to final value theorem s into this given function, 24 by s into s plus 2 s square plus 6s plus 5. Now substitute s0 in this function, then you will get 24 by 10, it is equal to 2.4. So that means the response follows 2.4 as time tending to infinity, means it is the steady state response. It is the steady state response and whose magnitude is 2.4. For the system shown in figure in the sixth problem, the steady state gain is given as 4 and the time constant tau is given 0.2 seconds. Then find the values of k1 and k2. So the steady state gain of this particular system described by the block diagram is given as 4 and the time constant is given as 0.2. And you can see that there are two constants involved in the given system. Now we need to find out value of k1 and k2. What is k1 and k2 when this data is given? So as you know that this closed loop system, we need to calculate C of s by R of s. You can consider this as g, consider this as h and g by 1 plus gh. So k1 by s by 1 plus k1 by s into k2. So this can be k1 by s by s plus k1 k2 by s, and this s gets cancelled and the function become k1 by s plus k1 k2. Let us write this in the time constant form. That means k1 by, take k1 k2 out, k1 k2 out, so it will be 1 plus s by k1 k2 and this k1 and k1 gets cancelled. So it can be 1 by k2 by 1 plus s into 1 by k1 k2. It is now in this form, that time constant form. I can say that this is some constant k by 1 plus s into tau, where k is the steady state gain, the value is given as 4 and the numerator is 1 by k2 here. So the k2 is now 1 by 4, 0.25, and the tau is the time constant. The coefficient of s is the time constant when you write in 1 plus s tau form. So the tau is 1 by k1 k2, where tau is given in the problem, the time constant 0.2. Now as you know, k2 you know already, 1 by k1 into 0.25 is equal to 0.2. So k1, now you can calculate, k1 is 1 by 0.2 into 0.25. Now so this is 25 into 250, so 1000 by 50, So, it is 20. So, this is the way you should calculate the constants when the data is given like this, steady state gain and the time constant. For the system shown in figure of 7th problem, omega n is given as 4 radians per second and damping ratio zeta is given 0.7. Then find the values of k, the steady state gain, and constant a in the feedback path. So, this is one of the problems on time response analysis, where undamped oscillations given as 4 radians per second and damping ratio is given as 0.7. You are asked to find out the steady state gain k and the constant a in the feedback path. So, as usual, we need to get the overall transfer function. This you consider as g and this you consider as h. So, this will be g by 1 plus gh form, and k by s into s plus 2 is the g by 1 plus g into h is 1 plus as. Now, you can simplify this and write in the standard form of second order system. As you know, omega n square by s square plus 2 zeta omega ns plus omega n square. Now, when you simplify this, k by s into s plus 2 by this comes to the numerator s into s plus 2 plus k plus kas by s into s plus 2. Now, this one and this one gets cancelled. So, this will be k by s square plus 2s plus kas. So, s can be common, that 2 plus ka, the coefficients of s, and then there is a constant k. Now, you can see that the numerator term is k, whereas with the standard second order system it is omega n square. So, k is equal to omega n square, where omega n is given as 4 radians per second. So, k value is 16. This is the way you should calculate the value of k is a steady state gain of the system for omega n 4 radians per second. Now, the another constant a you need to find out. So, you can see that s coefficient is this 2 plus ka, that must be equated to this 2 zeta omega n. So, 2 zeta omega n, where zeta is given and omega n is given, and k you have already obtained as 16. So, 2 plus 16a is equal to 2 into zeta is 0.7 and omega n is 4. So, this will be 5.6, 2 plus 16a. Now, 16a is 5.6 minus 2, that is equal to 3.6, and a is given by 3.6 by 16. This is the way you should calculate the value of a, the constant in the feedback element, and then the value of steady state gain when omega n and zeta are given. For the given non-unity feedback control system, in the problem 8, find out the steady state error for unit step input. So, let us look at the system that is given here. You can find there is a block in the feedback path. Consider this block as G, forward path gain, and this as H. Then This block diagram you need to convert into unity feedback control system, and the block in the forward path will be G by 1 plus GH minus G. You need to obtain this block to make this non-unity feedback control system into unity feedback control system. Now you need to proceed to calculate the steady state error ESS for unit step input given by 1 by 1 plus Kp, where Kp is limit s tending to 0 g of s. So you call this function as now g of s, and that is to be calculated for this given system. You consider this as g and this as h. So it is given by g means 100 by s into s plus 10 by 1 plus g is again 100 by s into s plus 10 into h is 1 by s plus 5 minus g, again that g is 100 by s into s plus 10. So this is the way you should evolve g of s for unity feedback system. You can see now, let us simplify this. S plus 10, no change in the numerator, and this LCM s into s plus 10 into s plus 5. So you have 1 here. So this s comes s plus 10 and s plus 5 as it is. Now for this second term it is 100, and for the third term s into s plus 10, so minus 100 into s plus 5. So you can see this s gets cancelled, s plus 10 also gets cancelled, and s plus 5 is there here, that comes to numerator, and in the denominator you have s. If you multiply these two factors, it becomes s square plus 15s plus 50 plus 100 minus 100s minus 500. Further simplification, 100s plus 500 in the numerator, and in the denominator you have s cube, then plus 15s square, then you have 50s here and 100s with minus sign, so minus 50s, then plus 100 minus 500, so minus 400 you get. So this is the g of s you get. Now you need to calculate the position error constant for this g of s. So this is given by limit s tending to 0 this whole function. So 100s plus 500 by this whole function s cube plus 15s square minus 50s minus 400. So when you substitute 0 in the numerator you have 500, and in the denominator all this will go and there is a minus here, so 5 by 4. The position error constant for this non-unity feedback control system you got minus 5 by 4. Now the steady state error is to be calculated using this formula 1 by 1 plus minus 5 by 4, and 1 by LCM is 4. So this 4 comes here, 4 minus 5 means minus 1. So this is equal to minus 4. So the steady state error for this non-unity feedback system is minus 4.